Hi everyone, welcome to the second part of video chapter 13 Polymers. In this video, we are going to continue the types of polymerizations. So we have the second types of polymerizations, which is the additions or change growth. So in this process, it involves monomers with one or more multiple bonds that are joined together by covalent bonds to form larger molecules without the loss of a small molecule. So this is a general formula of these additions polymerizations. And the R can either be a hydrogens, alkyl, aride, halogen, CN, OH, or an ester. So here's the two examples given. For these additions polymerizations, it can either involve only one monomer or it can involve more than one monomer involving multiple bonds. In these additions polymerizations, peroxide is used as the initiator. So homolysis of the weak oxygen-oxygen single bond of the peroxide will form the alkoxide radicals, which then add to a molecule of monomers to form a carbon radicals. So this is an example of the peroxide. So when these oxygen bonds break up, it creates these alkoxide radicals, which will then involve in the radical polymerizations. Okay, so imagine that the alkoxide radicals produced will attack the multiple bonds on its monomer, and then it will create a reactive site, which will then form a long chain of the polymers. So let's look at the additions polymers. We need to identify the structures of monomers, polymers, repeating unit, as well as the equations. So first example, we have polyethylene or polyethylene. The uses is to make foam, toys, plastic bags, container, and electrical installations. So this is a monomer of your ethene, and in the presence of this initiator, it will involve the formations of radicals. So the arrows we are using are single-headed arrows. So starting from the multiple bond or your double bond, so one of the electrons towards the left, another electrons towards the right, you open up the double bond and forming a polymers. So the structures given over here is your polymers. We have big brackets and an unknown N. So for an equations, there will be an unknown N for this monomer. So N monomers when it undergo polymerizations to form this long chain polymer. Another example here, we have polyvinyl chloride, which is known as PVC. The uses is to make pipes, siding, floor tiles, scooters, clothing, and toys. So the structures of PVC, you have this vinyl chloride. So again, in the presence of initiator or in the presence of peroxide, you're going to open up this multiple bond. So starting from the double bond, one electrons going to the left, another one going to the right, is just next to the double bond. And then you're going to form this polymer. So exactly the same structures, but now we are opening up this double bond. Okay, again, there's a missing N in front of this monomer to make a full equation. Example, we have polystyrene, or more commonly known as polystyrene, to make at carton, coffee cups, packaging, toys, electrical components. So this is a monomer structures of styrenes. In front of this monomer, we have the unknown N. So in the presence of initiator, we're going to open up this double bond. So one electrons to the left, another to the right, and you have this monomer structures. Okay, remember the double bond is just open up to the next bondings only. And the next example, we have Teflon. The uses is to make the coating on cooking utensil and electrical installation. So this is the structures of the Teflon, the monomers of the Teflon, and then you open up the double bonds, one to the left, to the right, and then forming the polymers. Okay, and take note that, okay, the double bonds now become single bond. And then at the left-hand side, right-hand side, there's still a new bonding. So you have a continuous long chain here. It just summarized into a symbol for this polymer. Next, going into synthetic rubbles is also one of the polymers. So it has some of the properties of natural rubbles, including being waterproof and elastic. So the synthetic rubbles, we produce it chemically. Usually you have an improved property compared to the natural rubble. Okay, it will be tougher, more flexible, and more durable. And it's normally used in wetsuit and tire. So this is the structures of your synthetic rubber. We have 1,3-butadiene. So to make an equation, so N in front of this monomer under the presence of initiator, or you can just label as peroxide. So for this one, starting from where you have the double bond. Okay, so 1 electrons to the left, 1 electrons to the right. So again, focusing on your double bond, 1 electrons to the left and 1 electrons to the right. So now you can kind of imagine that this double bond becomes single bond. This single bond will become double bond and then single bonds again. So for the polymers, you are going to draw a big bracket. Okay, single bonds and make a new bonds over here. It can have, it will have a CH2. And then single bond CH, single bond become double bond CH, and then double bonds become single bond CH2. And then close the bracket with the unknown N. Next, we have the example of this natural rubber isoprene. Okay, a structures of isoprene 2-methyl-1,3-butadiene. Again, in order to make a full equations, in front of this monomer, you have the unknown N. So focusing on where you have the double bond, okay, open up the double bond, half electrons going to the left, to the right, exactly the same for the examples before this. And then focus again on the next double bond. Okay, or this double bond, you're going to open up that double bonds again to the left, to the right. So the polymers that you're going to form, okay, a single bond CH2, double bond becomes single bond, the CH3 is still attaching over there, and then single bond become double bond CH2, CH, single bond CH2, and then continue with your remaining repeating unit. So here's the structures of the polymers, okay, involving the monomers with one or more multiple bonds. On the earlier examples, you are given monomers and then predict the structures of polymers. So if the questions give you the structures of a polymers, there is another way for you to predict the monomer. So to identify the structures of monomer, you need to start from the terminal bonding here. So that means the bonding near the big bracket. Alright, so use your half-headed arrows again. You are going to move in this single electrons. Okay, so for either side. Okay, move into the next bonding. And then you can look over here at this. Now you have a single bond together with one single electron. So we need to make a double bond at these positions and these positions as well. So you have to borrow this double bond. So you have to open up this double bond. So using a single-headed arrow, move into the positions where we want to reform the double bond. And then another electron is going to another side. So for this monomer, now it becomes CH2, single become double bond. And then you have this CH, double becomes single bond. And then single become doubles again, CH2. So this is the structures 1,3-butadiene just now we have. Okay, looking at this polyisoprene, okay, the natural rubber, also using the same method, starting from the terminal bonding. Okay, closing your bonding for both sides, and then you're going to use the double bond, okay, to complete the reformations of double bond over this. So now you can see that from single bond, it reforms the double bond. And then another single electrons go towards another bonding. So you have to complete this process so that you got a even number of electrons. Either it's two electrons or 4 electrons. So now the monomer of this polymers, you have CH2, double bond CCH3. This double bond will go back to the single bond CH, double bond CH2. Okay, a monomer of isoprene. All right, please have a try at this example questions number 1, 2, and 3, and we will discuss during our tutorial sessions. That's the end of our chapter 13. Please have a try at the exercises, and I'll see you again.